The last few sections of this course will be an introduction to differential equations. In this section, which I'm calling DE1, it'll be mostly looking at what a differential equation is and looking at some basic concept, solving some special differential equations. What this is this is a summary of chapter 9 in your textbook. So if you want more detailed information, you can always go to chapter 9. So let's look at what a differential equation is. When we talk about a differential equation, it's just an unknown function and its derivatives. So since the function is unknown, when you solve a differential equation, you're finding your unknown function. And since this equation has derivatives in it, typically the way that we get rid of a derivative is by integration. Now, going back to the very first semesters of calculus, remember that when we take a derivative, we have all these rules like quotient rule, product rule, chain rule. But when we integrate, we don't have those rules. Integration is tricky. You have to look at the type of integrand and you have to decide the technique based on the integrand. So you can't integrate products or quotients or using composition of functions in an integral. So that's going to be a problem when we solve differential equations. Since there's derivatives in there, typically we would integrate to get rid of the derivative, but we can't do that. So what we're going to do here is we're just going to look at differential equations, and then we're going to look at some special forms of differential equations that we can solve. Now, when you take a differential equations course, then you'll go into more complex differential equations to solve. So let's look at how we classify differential equations. Well, one thing we could do is we could talk about the order of the differential equation. So when we talk about the order of a differential equation, it's just the order of the highest derivative. So if there's a third derivative in the equation and that's the highest derivative, then it would be a third order differential equation. Another thing we can do is state whether the differential equation is linear or not. If it's linear, then the function y and its derivatives are in the first power and not composed with other functions. So there's no products or quotients of y and its derivatives. In example 1, it says to state the order of the differential equation and state whether the equation is linear or nonlinear. So y prime of x is equal to cosine of x plus 3y. So notice that I have a first derivative, and that is the derivative of highest order. There's no second derivative or third derivative. So since we have this first derivative, it's a first order differential equation. So is it linear or is it nonlinear? Well, when I look at the function y and I look at the derivatives, they're not composed with other functions. They're not products or quotients with other functions. So this is actually linear. So the next equation is y prime of x is equal to cosine of y plus 3y. Again, the highest derivative is a first derivative, so it's a first order differential equation, but it's actually nonlinear. And it's nonlinear because of cosine of y. That's a composition of cosine with the function y. So since that's a composition of our function y with another function, it makes it nonlinear. All right, so what about this second derivative of y with respect to x equal to y squared minus sine of x? Well, there's a second derivative, and that's the highest order. So this is going to be a second order differential equation. Now, is this linear? No, this is not linear, not because of the sine of x. It's because, remember, it's the function y. The function y is y squared, so it's actually y times y. So that's a product of a function with itself. That makes it nonlinear. So this last equation, differential equation, has a first derivative, highest order, so that would be first order. And then on the right-hand side, you see x times y. This is actually linear. To be nonlinear, y has to be composed with another function. X is not a function, it's the independent variable. So there's no products or quotients of y or its derivative. So this is actually linear because y is not a product with another function. It's a product with the independent variable x. All right, so the next thing we're going to do is we're going to start solving our differential equations. Example 2, we want to solve the initial value problem, and this seems so simple after going through Calc 4, because we're actually going back to single variable calculus when we talk about these differential equations. So if we want to solve the initial value problem, y prime of x equal to cosine of x plus 3x, and then we have the initial condition that y of 0 is equal to 2, well, solve means, what is y? What is my function y? Well, I could simply integrate both sides. If I take the integral of y prime, and here I'm integrating with respect to the variable x, so I'm allowed to integrate both sides. And then on the left-hand side, remember y prime is dy over dx. So the dx would simply cancel. And we would have, let me write this out for you. So you could see here that these dx's would cancel, and I'm just integrating with respect to y on the left-hand side. Now on the right-hand side, this is simply going to be sine of x, because I'm integrating with respect to x, plus 3x squared over 2, plus some constant c. Now, if you're integrating both sides of an equation, you only have to put the constant on one side. On the left-hand side, the integral of dy is simply y. Remember, y is a function of x. This would be the general solution, but I have some initial conditions, which allows me to solve for my variable c. So y of 0 equal to 2 means that when x is 0, y is 2. This becomes sine of 0 plus 0 plus c equal to 2. And my c value is equal to 2, which gives me solution y of x equal to sine of x plus 3x squared over 2 plus 2. And I've solved my differential equation. In example 3, there are no initial conditions, so we're just going to be finding a general solution, which means I'm still going to have my constant c in my solution. But this is a second order differential equation. This is a double integral. So I'm going to have to integrate twice. I'm going to do what I did before. I'm going to integrate both sides with respect to x. And on the left-hand side, this just becomes first derivative. I have x to the third minus 2x squared plus 6x plus c. All right, so I need to find y. I'm going to integrate again. Integrate with respect to x on both sides. And I already have this constant c, so when I integrate, I'm going to have to choose a different variable. On the left-hand side, this becomes y of x is equal to x to the fourth over 4 minus 2x to the third over 3 plus 6x squared over 2, so that would be 3x squared, plus cx, plus a constant, I'm going to call it d. And that would be the general solution. I cannot find explicit solution because I don't have any initial conditions. One way to look at solutions for differential equations, and here we're looking at general solutions where you still have that constant, so you're going to have like a family of solutions, is to look at what we call a direction field. Now, when we talk about a direction field, it's similar to a vector field, except for there's no arrows. They're just little tiny lines. And actually, these little lines kind of represent what a tangent line would look like at any point. But here we're going to assume that our independent variable is t, and our function is the function y. But, you know, it's just a variable. It could be x, it could be u, it could be anything. What this is going to give us, this direction field, is it's giving us all the solutions to a differential equation. Now my differential equation is given here as y prime of t equal to y minus 2. So that's my differential equation. These are all the possible solutions. So notice that if I started here at between maybe 2 and 2.5 and I sort of followed these little tangent lines or these little slopes, I would get a solution. And that would be the solution with the initial condition that t is 0 and maybe y is about 2.3. That would be one solution. So you could pick any point in this direction field and just follow the slopes, and that will be a solution for that initial condition. In example 4, it says for what conditions at t is equal to 0. So we're going to look at starting here at 0, which would be our y-axis. For what conditions at t equal to 0 are the solutions constant, decreasing, and increasing? Well, the solution is constant when your slopes are little horizontal tangent lines, which would be at 2. So that would be when y is equal to 2. If you look at that differential equations, you see if I put in 2 for the y value, the derivative is equal to 0, which means that the tangent line is horizontal, which means that the function has to be constant. So we have constant solutions. When y prime of t is 0 is what we're looking at, is equal to 0, which would mean that y minus 2, I don't have to do all this algebra, I'm just showing you where I got the algebra from. So when y is equal to 2, you have constant solutions. So you're just setting your derivative equal to 0. Decreasing, which decreasing just means that the derivative is negative. So let's look at where the derivative is negative. So decreasing means this derivative, and we're looking at t is equal to 0, is less than 0 or negative. So that would be when y minus 2 is negative, which would be y less than 2. And you could see that if you pick any y value that's less than 2 and you follow the slopes, you get this solution that's going down. All right, so where is it increasing? Increasing when the derivative is greater than 0 or positive. And that happens when y is greater than 2. So look at that line that we had written before. That would be a specific solution to the differential equation, y prime equal to y minus 2. Given those initial conditions, it would be an increasing function. So that would be a picture representation of all the possible solutions to a differential equation, and that's assuming that you don't have initial conditions. So let's look at example 5. Consider the differential equation y prime of t equal to y times y minus 2. Part A, for what initial conditions, y of 0, so that means t is equal to 0. So y of 0 equal to a is the solution constant increasing or decreasing. Sketch the direction field. Sketch the solution for the initial condition y of 0 equal to 1. Okay, so A. We want to figure out for what a value is the solution constant. Increasing and decreasing. Well, if it's constant, that means the derivative is equal to 0. So that means that y times y minus 2 has to equal to 0. That happens when y is equal to 0 and y is equal to 2. So these are my constant solutions. Now remember, this is a derivative. So if you just look at the derivative, and let me go ahead and just draw a line graph. Look at those two values of 0 and 2. So those constant solutions are when the derivative is equal to 0. So that means that all other points are where the derivative is either positive or negative. So if you put in values that are less than 0, y values less than 0, then look at this product. You'll have a negative. If y is less than 0, it's going to be a negative times a negative, which means this is going to be actually positive. So it's going to go up. If you pick a value between 0 and 2, say 1. And if you put 1 in for y, you get positive times negative is negative. So it's going to go down. If you put in a value greater than 2 for y, such as 3, then you get positive times positive is positive, oops, and the derivative is going to be positive there. So it's going to go up. So we could see that it's going to be increasing when y is less than 0 and y is greater than 2. Okay, so it's decreasing when y is between 0 and 2. Okay, and it's constant at 0 and at 2. Let's go ahead and sketch the direction field. You know how I am about drawing, right? Pretty horrible. I'm going to go ahead and look at my graph. My variable is t and y. So the first thing I'm going to do is, and this is how I always do my direction field, I'm going to look at my constant solutions first. So at 0 and at 2. That means if I were to, and here I'm going to draw my direction field in a different color. So if I were to draw that direction field at 0, it would be horizontal tangents, and also at 2. So again, this is just a sketch. It's not going to be beautiful or anything. Now remember that it's increasing when y is greater than 2, decreasing between 0 and 2, and increasing less than 2. So if we look at greater than 2, increasing means that these slopes are going to start getting larger and larger, or steeper and steeper and steeper. So you would just simply look at a steeper slope because it's increasing, and then just keep getting steeper. You notice how fast I'm writing this and it's really sloppy, which is fine, right? You just want to get an idea of what the solutions would look like. So you're just getting steeper and steeper and steeper, and it's going to continue to increase for y values greater than 2. So between 0 and 2, it's decreasing, and it's always decreasing. So you have to draw going down, but always going down. Sorry. And then it's approaching the 0. So that's always decreasing. And then increasing for less than 0. So again, tangent lines going up. And so sad, but you get the idea. Okay, so there's my sad field, and that was B. So part C says sketch the solution for the initial condition y of 0 equal to 1. So that means t is equal to 0, y is equal to 1. Let me go to that point. T is 0, y is 1. That would be this point here. I need to draw my solution curve, so I'm just going to follow my sad direction field. And that would be just a rough sketch of the direction field and that particular solution, that particular function that gives a solution for those initial conditions. Now we're going to actually solve some differential equations of special form. The easiest type of differential equation to solve would be a separable differential equation. Now, when we talk about separable differential equations, and here we're just going to be looking at first order differential equations, which is why I call this DE1 for first order. So a separable first order differential equation is just a differential equation y prime equal to some function, where that function may involve both variables, x or t and y, but as long as we can separate it and bring all the y's to the left-hand side and all the t's to the right-hand side, then it may be solvable. And the way we're going to solve it is the method we used in the very beginning when we integrated both sides. So if you can take a differential equation, stick all the y's on one side, all the t's or x or whatever variable we're talking about on the other side, then you can just simply integrate both sides. So example 6 says determine if the equation is separable. If so, find the general solution. So if it is separable, I should be able to move all the y's to one side, keep all the t's on the other. I notice that if I simply multiply both sides by 4y squared, then I have 4y squared times y prime of t is equal to e to the t. So yes, it's separable. I just separated it so that the y's are one side, the variable t is on the other side. And at this point, I could simply integrate both sides. Now remember that y prime of t is the same as saying dy dt. And we are integrating both sides with respect to the variable t. So both sides are going to be dt. You cannot integrate with respect to one variable on one side and another variable on the other side of an equation. Whenever you have an equation, you have to do the same thing on both sides. So if I integrate the left with respect to t, I have to integrate the right with respect to t. But something nice happened. Notice that the dt's cancel, similar to what we did in that the second example, third example. And we're simply integrating 4y squared with respect to y. Now on the right-hand side, this is simply e to the t plus our constant c. On the left-hand side, this is going to be 4y to the third over 3 equal to e to the t plus c. I'm almost done. To solve this differential equation explicitly, I have to solve for y, get the y by itself. I'm going to multiply both sides by 3/4 to get y cubed equal to 3/4 times e to the t plus c, and then simply cube root everything. And this is the solution. Sometimes, and notice that this is just a general solution because I don't have initial conditions. I can't figure out what my constant c is. So sometimes you can explicitly solve for y and get it by itself. Sometimes it's difficult. It depends on what functions you have. Let's go ahead and do another example. Let's determine if the equation is separable, and if so, we're going to solve the initial value problem. So in this case, we're going to solve for a constant c, assuming it's separable. If I simply divide both sides by y squared, then I get y prime of t over y squared is equal to 1 over t squared plus 1. So yes, it is separable because I just separated it. Integrating both sides, I'm going to skip the step where I write this as dy over dt and cancel the dt's. Since I know that the dt's will cancel, I will simply write this as, and I'm going to write this as y to the negative 2 dy equal to the integral 1 over t squared plus 1 dt. Now, notice that I'm integrating with respect to different variables on both sides, but in this case it's okay. I'm just skipping that step where the dt's cancel as we did in example 6. So now we have y to the negative 1 over negative 1, which would be negative 1 over y, equal to 1 over t squared plus 1 is tangent inverse. So this is tangent inverse of t plus some constant c. Now I can simply multiply both sides by y, then divide by tangent inverse and so on. But I think I'm just going to flip both sides of the equation. And this becomes 1 over tangent inverse of t plus c on the right. And distribute that negative. So y is equal to negative 1 over tangent inverse of t plus my constant c. That's just my general solution. I do have my initial condition that y of 0 is equal to 2. So what that means in this equation is that y is 2, negative 1 over tangent inverse of 0 plus c. So tangent inverse of 0 is simply 0. This is going to be a negative 1 over c. So if 2 is equal to negative 1 over c, that must mean that c is equal to negative 1/2. My explicit solution, y equal to negative 1 over tangent inverse of t minus 1/2. Now I am going to stop here. Just be aware that on my lab, since this is a complex fraction, we have that half in the denominator, they may want it to be simplified. And in fact, this is a negative, and there's a subtraction in the denominator. So we could simplify it some more to get y equal to multiply top and bottom by 2 to get rid of the fraction, and then distribute that negative to get 2 over, change the order to 1 minus 2 tangent inverse of t. Okay, so that's just a caution that your MyLab may want you to simplify it even further. And that's what we call a separable. Now it could happen that you have multiple initial conditions, and that just means that you're going to find a general solution, and then if you have more than one initial condition, then you'll probably have more than one solution. In example 8, we want to determine if it's separable. If so, solve the initial value problems, because there's more than one. And yes, this is separable. I can write this as e to the y. If I divide both sides by e to the negative y, it becomes e to the y. This becomes e to the y times y prime of x, and here are the variables x naught t equal to cosine of x, so yes, it's separable. And now when we integrate with respect to x, the dy, dx is going to cancel. This becomes the integral of e to the y dy. And on the right, we have the integral of cosine of x dx. Integral of e to the y is simply e to the y. And then cosine of x is going to be sine of x plus c. All right, so now it gets a little tricky. To solve for y, I need to natural log both sides. But you have to remember that when you do natural log both sides, you need absolute values around the expression because natural log can never be negative. However, e to the y is never negative because our base e is positive. Any exponent, it's still going to be positive. So I don't actually need absolute values on the other side as well, because if the left-hand side is always positive, then the right-hand side will always be positive as well. Now you may want to put the absolute values on, which is fine. And now whether you have absolute values or parentheses, it doesn't matter to me. It may matter with MyLab though. So the natural log of e to the y is just y. And this is natural log of sine of x plus c. So I don't believe MyLab wants absolute values on there. This would be an explicit solution, but we have two conditions. So let's look at the first condition. The first condition says y of 0 is equal to 1. So if y of 0 is equal to 1, then e to the 1 is equal to sine of 0 plus c, which means c is equal to e. And we have the solution y equal to natural log of sine of x plus e. What about the other condition? Y of pi over 2 is equal to 1/2. So that gives us e to the 1/2 is equal to sine of pi over 2 plus c. Sine of pi over 2 is 1. So we have e to the 1/2 is equal to 1 plus c. That gives us a c value of e to the 1/2 minus 1. And we get our solution y equal to natural log of sine of x plus e to the 1/2 minus 1. And we also had another condition, y of pi equal to 0, which would be e to the 0 equal to sine of pi plus c. And that tells me that c is e to the 0 is 1, sine of pi is 0, so c is equal to 1. And I have the solution y equal to natural log of sine of x plus 1. So you could have more than one initial condition. Now, sometimes it is easier to not solve a differential equation explicitly for y. So let's go back up to our general solution. Maybe I would have preferred to keep it as e to the y equal to sine of x plus c. So that would be an implicit solution because I haven't explicitly solved for my y value. That's what we're going to talk about next. We're going to talk about implicit solutions because sometimes it's actually easier to leave solutions as implicit. Example 9, we want to solve the initial value problem. Y prime of x times sine of y is equal to cosine squared sine of x. And we have some initial conditions here too. So first of all, this is already separated. I can just integrate both sides. On the left-hand side, the dy dx will cancel, and this simply becomes the integral of sine of y dy equal to integral of cosine squared x times sine of x dx. And here you could do a substitution maybe on cosine, or if you wanted to try a trig identity and replace the cosine squared with something, you could do that as well. I think you'd still need to do a substitution anyway. So what I'm going to do is I'm just going to do a substitution on the right. I'm going to let u equal cosine of x, which gives me du equal to negative sine of x dx, or du negative du is equal to sine of x dx. On the left-hand side, this is negative sine, or negative cosine, sorry, of y. And on the right-hand side, it's a negative du, so it's going to be a negative integral of u squared du. And I'm just going to go ahead and cancel the negative on both sides. I have cosine of y equal to u to the third over 3 plus my constant c. However, I have to put the u back to get cosine of y equal to cosine cubed of x over 3 plus c. Now here, I'm going to keep it in an implicit form because notice to get the y by itself, I have to take cosine inverse on both sides. Now, once I take cosine inverse, I have restricted my domain because cosine inverse is restricted where cosine of y is not. So I'm going to choose to keep this in implicit form. Again, because I don't want to do cosine inverse on both sides, because that will restrict my original domain. From here, I'm going to look at that initial condition y of 0 is equal to negative pi over 3. So if y of 0 is equal to negative pi over 3, then cosine of negative pi over 3 is equal to cosine cubed of 0 over 3 plus c. 1/2 is equal to 1/3 plus c. So 1/2 minus 1/3 is 1/6, I believe. And my solution is cosine of y in implicit form is equal to 1/3 cosine cubed of x plus 1/6. And again, I'm going to leave it in implicit form because I don't want cosine inverse on both sides. An application that comes up a lot with separable differential equations is what we call a logistic equation. So a logistic equation is just simply a population equation, and it comes up a ton. In example 10, we have 100 flies. They're in a jar. We're going to let P of t be the number of flies in the jar t days later. The population may be modeled by this differential equation. So we're given this differential equation. We're told that t is going to be greater than or equal to 0 because here t is actually time. And the initial condition is the population at t equal to 0 is equal to 100 flies. So we're going to find the general solution. We're just going to do this once. Once I have found the general solution to a logistic equation, you can always just use it. Let's see. So our differential equation is separable. I can bring the p times 1 minus p over 600 to the left-hand side and write it as 1 over p times 1 minus p over 600. So here I'm just separating it, dp dt, and that's going to be equal to the 0.1. So I got all the p's on one side, and I'm going to integrate both sides. This is hideous, but I am going to do some simplifying. It becomes dp because the dt's cancel, and then integral of 0.1 dt on the right. So if you use partial fraction decomposition from Calc 2, the integral on the left is actually going to be 1 over p, once I've decomposed it, plus 1 over 600 minus p. Again, we're just using partial fraction decomposition from Calc 2. And then I have 0.1 t plus c on the right-hand side. So the integral becomes natural log of, and I'm going to keep the absolute values around this p because I really don't know what p is. Even though it is population, so it's never going to be 0. So I actually don't need the absolute values, but I'll keep them on for now. This actually becomes a minus because it's a 600 minus p. It's not p minus 600. Natural log, absolute value of 600 minus p equal to 0.1 t plus c. And now I'm subtracting, same base with the natural logs on the left. I can actually write this as the natural log of absolute value of p over 600 minus p. And again, I'm just keeping the absolute values on. Okay, so I'm supposed to be solving for p. If I exponentiate both sides, that'll get rid of my natural log, and I'll have absolute value of p over 600 minus p is equal to e to the 0.1 t plus c. And now remember what we can do here. When you're adding exponent algebraically, this is e to the 0.1 t times e to the c. Also, on the right-hand side, it's base e. That base e is never going to be negative. So I know I don't need the absolute values. Since the right-hand side is always going to be positive or 0, then I'm okay with the dropping the absolute values since it's not going to be negative. So this is e to the 0.1 t times e to the c. Now e to the c is just a constant. So I'm going to call this d. All right. P over 600 minus P is equal to this constant D, e to the 0.1 T. Remember, my goal is to solve for P. I'm going to go ahead and multiply both sides by 600 minus P to get rid of the fraction, and then I'm going to go ahead and distribute. So P equal to 600, well, d e to the 0.1 t times 600 minus p. And then on the right, if I distribute the d times e to the 0.1 t and get rid of the parentheses, then I would have, and then I can also add p d e to the 0.1 t to both sides. Let me skip down to p plus p times d e to the 0.1 t, so just a bunch of algebra, equal to 600 times d e to the 0.1 t. Okay, now I'm trying to get the p by itself, so it looks like I could factor out a p on the left to get 1 plus d e to the 0.1 t in parentheses. And now it's simply a matter of dividing both sides by what's in the parentheses to get the p by itself. So a ton of algebra. All right. So I've actually solved this for my function p. Oftentimes, though, when you're solving these kind of equations, you notice that we have this expression, this d e to the 0.1 t in the numerator and denominator. So algebraically, if we just simply divide top and bottom by d e to the 0.1 t, we could write this in a more efficient way as p equal to 600 over d e to the negative 0.1 t plus 1. This would be the general solution in its simplest form. Now b, I'm going all the way back up. Part B says solve the initial value problem. So we have P of 0 equal to 100. Which would give me 100 equal to 600 over d plus 1. And then solving for d, I have d plus 1 is equal to 6 or d is equal to 5. So my initial value problem, the solution is going to be P of t equal to 600 over 5 e to the negative 0.1 t plus 1. Okay, now notice on the bottom here, it says special first order linear differential equations. That actually should be on this next page. Sorry about that. So we're going to look at another type of differential equation. So we had separable. That just means can you get the function, its derivative on one side and the variable on the other side so that you can integrate both sides directly. But there's also this other form. I just call it the KB form. if you have a first order differential equation of this form here, if you can write it as the derivative equal to some constant k times the function plus a constant b, which is why I call it the kb form. If you can write the linear equation or the differential equation this way, then the solution is y equal to c times e to the kt minus b over k. So c is just going to be our arbitrary constant. Example 11 says solve the initial value problem. So I'm going to try to get it into that form by getting the derivative by itself on one side, y prime of t. So I'm going to add the 2y, and I'm going to subtract 8 from both sides to get derivative equal to 2y minus 8. So this is of that form. Notice that k is the coefficient on the y value, so in this case it would be a positive 2, and b is negative 8 because it's supposed to be plus b, but it's a minus 8, so b is actually negative 8. My solution, the general solution, is simply c times e to the 2, so kt, so 2t, plus, it's a minus, but b is negative, so it'd be a plus, b over k is just 4. So if you do have a differential equation of that form, then this is going to be the general solution. In this particular problem, we have the initial condition that y of 0 is equal to 0. Which gives me 0 is equal to c plus 4, so c is equal to negative 4. And then my solution is y of t equal to negative 4 e to the 2t plus 4. So in this section, DE1, we're looking at the basic idea of what a differential equation is, looking at those direction fields, and then looking at two special types of differential equations that we can solve pretty easily, and that would be the separable, and now here we're looking at the KB form. So what we didn't talk about when we were looking at direction fields is what an equilibrium solution is. So when we talk about equilibrium solutions, that just means the constant solution. Now there's two types of equilibrium solutions. One of them would be in this first box here. This is going to be a stable equilibrium solution. And the reason why it's a stable equilibrium solution is because look at the equilibrium solution, and that would be the solution here. This is our equilibrium. That would be where you have your constant solution. So near our equilibrium solution, all the curves approach the equilibrium solution. So if all the curves approach the equilibrium solution when you're near the equilibrium solution, then it's stable. However, if you have an equilibrium solution and the solutions go away from your equilibrium solution, then we say that it's unstable. So to be stable, you have to approach from both sides, or just one side if the particular problem you're working on doesn't maybe include negative t-values or something like that. In example 12, we want to find the equilibrium solution. We're going to make a sketch of the direction field and determine whether the equilibrium solution is stable or unstable. We're going to do what we did before. We're going to first find our equilibrium solution, which is simply the constant solution. So that would be where this derivative is equal to, where the derivative is equal to 0, right? So I'm solving the equation 0 equal to negative 1/2 y minus 1. and that will give me negative 2 is equal to y. That would be my equilibrium solution. All right, so as before, we want to determine what our direction field will look like. We write down all the equilibrium solutions on a number line, and we look at our derivative. If we put in y values that are less than negative 2, then our derivative is going to be positive. If we put in y values that are greater than negative 2, and you could put in 0, right, and it's going to be negative, that tells me what my graph is going to look like. My equilibrium solution is at negative 2. So that's my horizontals. Greater than negative 2 would be negative. So my solutions are going to approach. They're coming down, right? Oh, such a sad sketch, but you get the idea. And that's fine. I don't need to graph anymore. And below negative 2, they're going to go up and approach. Okay. So the question is this stable or unstable? And this happens to be stable because my solutions are approaching my equilibrium solution. So stable, I want blue. In example 13, we're going to do an application. We have a drug that's administered intravenously. We have a rate of 5 milligrams per hour. The amount of drug in the bloodstream in milligrams can be modeled by this initial value problem. So this is a very common type of problem where you have a derivative and you have its function, so it's a differential equation. Y prime is equal to 0.03 y plus 5. So we have an initial condition. T is in hours. Part A, we want to find the solution to the initial value problem. First of all, notice that this particular differential equation is in the KB form, where K is equal to negative 0.03 and B is equal to 5. So I already know what the solution is going to look like. It's going to be y of t equal to c e to the negative 0.03 t plus, because k is negative, it's going to be a negative negative, so plus 5 over 0.03. And I think that I don't like having a decimal in a fraction, so I may write that as 500 over 3, just because it's going to bug me. All right. Okay, that makes me feel better. Solving for C, I have is 0 equal to C plus 500 over 3, and my C value is going to be equal to negative 500 over 3. Y of t is equal to negative 500 over 3 e to the negative 0.03 t plus 500 over 3. Great. Again, don't have to do this, but I see that I have a 500 over 3 in both terms. So I'm going to factor out, the 500 over 3, and I'm also going to change the order because it's going to be a minus e plus 1. So I'm going to write it as 1 minus e to the negative 0.03 t. This would be the solution, and Y is in milligrams, by the way. So we might want to remember that. Part B, what is the steady state or equilibrium level of the drug? So when we talk about the equilibrium level, in this particular problem, when we're talking about administering drugs, that's called the steady state solution or level. That would mean that the amount of the drug going in equals the amount of the drug going out. So when we find the steady state solution or the equilibrium solution, remember, all we're finding is where the derivative is equal to 0. So I'm going to go back to my differential equation and simply set it equal to 0. So that would be when Y is equal to 500 over 3. And this is in milligrams. Y is in milligrams. So when we have 500 over 3 milligrams of this drug, then that means that the same amount of drug going in equals the same amount of drugs going out of the bloodstream. Okay, so that would be our steady state solution. And here I still have my units on there. C says, when is the drug at 60% of the steady state value? Maybe I'll come back up and look at part C. So C is saying, okay, 60% or 0.6 of our steady state value, which is 500 over 3. We want to know when this is going to happen. So that's what we're going to set our differential equation in solution to the differential equation in part A equal to. So that's going to be equal to 500 over 3 in parentheses 1 minus e to the negative 0.03 t. Again, that's milligrams. Notice that the 500 over 3 can cancel on both sides. So this is the equation that I'm solving. Let's see if I add the e to both sides and divide by, or subtract. Ah, gotcha. So it looks like it's going to be e to the negative 0.03 t equal to 0.4 because it becomes 1 minus 0.6. Natural log both sides, and I get negative 0.03 t equal to the natural log of 0.4, and then divide by the negative 0.03. Notice that I haven't used my calculator to approximate any values. Typically, you don't do that until the very end. So at this point, I would plug this into my calculator to get t being approximately equal to, I'll go 1 decimal point, 30.5. And this was time, so this is hours. So approximately 30.5, 30 and a half hours. That's when it'll be 60% of the steady state value. Now that's it for this section. In our next differential equation section, we're going to look at some special second order differential equations. So this is it.